Okay, uh, we're going to continue with the interference of wave. Last time we talked about the interference of wave for the wave on water surface or river wave, right? That the case for two dimension in the space, let's say. Okay, next we're going to talk about the interference of wave on a string. That is one example, or let's say classic example for one dimensional wave. Okay, as you know that wave speed, I mean, first of all, we're gonna have to talk about the wave speed for the wave on the string. You know that wave speed for any type of wave depends on the properties of the medium. Uh, that also true for the wave on the string that I already mentioned. Uh, the wave speed equal to the square root of the string tension divided by the mass density. And for the case of one dimension, mass density should be kilogram per meter. All right, and tension, you know, this is a force, right? So it should be Newton. Okay. And the next thing about wave on the string is that if you want to create a wave on the string, so one side of the wave should be fixed. Or fixed can be either means that it's not allowed to move up and down. We call that case is fixed end. It's fixed, so it's not moved. That side of the string is not moved. The other case we call losing end. Losing end means that it's fixed, but it's allowed to move up and down freely. For ideal case, it's move up and down without any loss in energy. That we call losing end actually. You know that if one side is not fixed, you cannot make a tension and cannot create the wave on the string. That's what I mean to say. Okay. Next is what is really interference of wave on the string. So it can be either wave moving in the same direction or a wave moving in different direction. And this slide gives you an example. If we have pulse wave that both of them having the same phase, so you see that their displacement is on the positive vertical direction. When they combine, so you get the double of the amplitude. That is, and after that is they just separate, moving the way they moved before. If they have opposite phase, so one up and one down, so you know that when they meet at the middle, there is no, so it is zero displacement, and then they just move the way they are. Okay, that quite simple things to mention. That pulse wave is quite easy to understand, but how about the periodic wave? Okay, when we deal with the periodic wave, you know that wave is continuous. The most easy way, you know that you can write the wave function, right? Like in the form of y xt equal to the amplitude or maximum displacement multiplied by psi kx minus or plus omega t, depending on the direction of the movement, something like this. And what is really the mean of interference? In fact, what to deal with the interference? It's just the combination of the two wave function. You have wave 1 and wave 2, and you say, okay, the combination is a sum of wave 1 and wave 2, and that just is, you know, it's also true for the wave like ripple wave, that you deal with the two-dimensional wave, or even some other type of wave like sound wave that you deal with the three-dimensional case, they are the same. If you can write the function, you can really find the net wave or the resultant wave or whatever you want to call. But that is the result of the interference of the wave you have. Okay, so in more than one dimension, you might write the wave function this way: yrt equal to ym psi k. That become vector, right? More than one dimension, you know, and or k dot r plus minus whatever omega t. Okay, this is the way. If you can write the wave function in this form, so you can simply find the interference wave by sum up the wave function directly, and that what we call, actually why we call this superposition, because it's just superposition of the wave function in the space. That's the result of the interference of the wave. Okay. Yes. So that would be case. I mean, in this case, it's quite simple because you know that in one dimension, wave can move either. I mean, if you have two waves, and you want to find the interference of these two waves, there would be two cases. One is they move to the same direction, for example, like positive x, or the other case is they moving to the opposite direction, one to the positive x and the other to the negative x, right? Okay, let's deal with the first case. When the wave traveling to the same direction, in this case, y1 is here moving to the positive x, y2 also moving in the positive x. So you sum up, you want to find the resultant wave. I will call resultant wave after this. Okay, resultant wave equal to y1 plus y2. You just plus the mathematical function directly like this. Okay, of course, it might not be simple if you see that if k and omega are different, right? But it's quite simple. Okay, let's say if for example also the amplitude are different, you might not get this easily. But okay, let us only try with the most simple case when two waves getting the same wavelength or wave number, and they have the same frequency, so the same omega, right? You know, k is 2 pi divided by lambda, and omega is 2 pi f, or 2 pi divided by the period. Okay, I don't need to repeat that. But you see that in this case, okay, and y and the amplitude of two waves also the same, but only different is the phase. One has a phase of 0 and the other have a phase of phi or phi, like this. Okay, so you can using symbol the mathematic formula psi alpha plus psi beta equal to 2 psi alpha plus beta divided by 2, and cosine alpha minus beta divided by 2. You can find from Google, and you can combine them and get the form like this. Okay, I would say that what really is this? It's just a sum up two function and you make it the most simple form, right? That has two parts. One is this part, sine kx minus omega t plus half of the phase. You see that this is actually the characteristic of wave, right? While you have a sine or cosine function and you get kx and omega t inside, this is wave, okay? Or you can say this is continuous wave. What really is this? 2ym cosine half of the phi. This is, you know that the phi is constant, right? When the phi is constant means that, oh, sorry. When the phi is constant means that 2ym cosine phi also constant. This is a new amplitude, right? New amplitude. And another term is characteristic of wave, right? Wave characteristic. Okay. Nothing special. So what I would conclude here is that the combination of two waves that moving to the same direction is a wave. But it change in the amplitude and change in the phase. I mean, the phase will be half of the phase difference of the two. Okay. And you see that the amplitude is dependent on the phase difference, right? You can really check up here. Okay. If the phase difference is, let's say, 120 degree, you get that, you know, cosine 60 get you a half, so the amplitude will be the same. I mean, you get the combination with the amplitude that equal to one of the component wave. Okay, and when the phase difference is zero, of course they are in phase. They are in phase means that you get double of the amplitude of the new wave, and so on. This is nothing complicated, right? But okay, another case is when they get the opposite phase. So means that the phase difference is pi. What you get is a total or destructive or fully destructive interference. So you in this case, you will see no displacement at all. On any position of the string, there's no displacement. There's no wave, let's say. Okay, and actually that is for the first case. And okay, we have some exercise that you're gonna try by yourself. I will get you the solution for all the exercise, but let's try. Okay. Okay, the first one, you know that the wave can be defined also by the cosine function. Of course, just do some practice if you know how to really combine the two waves in the cosine form, because I already gave you the example in the sine form, right? And you can get also a similar mathematical formula to combine two cosine function. Okay, okay, the rest, I give you one example of the exercise. Okay, you have two waves like this. This is still in the sine form, and you know the phase difference is 0.8 pi, right? You get the two waves with the same amplitude, same wave number, same omega or angular frequency. You can really go back to the slide, and you know that okay, my new amplitude is 2ym cosine half of the phase difference. So you can say that okay, y prime xt equal to 2ym cosine half of the phase multiplied by sine kx, in this case minus omega t plus half of the phase. Oh, sorry, I write on the wrong. It should be here. Okay, sorry. Should be on this exercise, not the other verb. Sorry. Okay. Again. Okay. Is y plum xt equal to? You can already say this is. Okay, I should write it like this first. 2ym cosine half of the phase and sine kx minus omega t plus half of the phase. Okay. What is the amplitude of the resultant wave? It's just exactly this one, right? So in this case, 2 multiplied by 5.6 millimeter and multiplied by cosine of that 0.8 pi divided by 2. This is very simple. Okay. Okay, I will not do the calculation for you. You can do this by yourself. And what is the phase angle relative to the wave1 of the resultant wave? Because wave1 has no phase constant, right? Or you can say that wave1 has a phase constant of 0. So the difference should be this one. So is phi divided by 2, or you can say that this is 0.8 pi divided by 2, or is 0.4 pi. Okay, if the third wave of the amplitude 5 nanometer is also be sent along the string in the same direction and at the first two, what should be its phase angle in order to maximize the amplitude of the new resultant wave? You might say, okay, now we deal with the psi function with different amplitude. How could we do that? You know, this two has like 5.6, this one also, this one 5.6, and this one also 5.6, and we have a new wave with 5 millimeter amplitude. Well, you don't need to be panic. You know that the addition has what you say that, I mean, now I will call it y palm 2 xt should equal to y1 xt plus y2 xt plus yt xt. You get the resultant wave of y1 and y2, right? And we get y3 here. But the question asks you only what is the phase angle for the y3. That's gonna get the maximum amplitude of this y2 palm. Just simple, right? You know that if the wave have the same phase, so they get you maximum amplitude. In this case, you know that the resultant wave, so y1 plus y2 or y prime here, getting the phase of 0.4 pi. This one should have also 0.4 pi in order to get in phase. The y prime, right? Xt. Understand what I mean, right? So this the answer. Should they the third wave should have the same phase as the combination of wave 1 and wave 2. That is okay. I think I will leave this question for you. Okay, let's try by yourself.